these three concepts, which they look like a lot, but let's go over them slowly. So we know that diastole refers to the phase where the heart relaxes, and systole refers to the phase where the heart contracts. And we know that ventricles are the ones responsible for contraction and relaxation. So if we put those all together, and diastolic ventricular volume refers to the amount of blood that has remained within the ventricles after diastole, after relaxation. Right? In the same way, this also refers to ESVV, the amount of blood that remains within the ventricles after the end of the systole or the contraction. Alright? And then we have ejection fraction. What does this mean? So ejection fraction is basically the amount of blood. It refers to the percentage. If stroke volume refers to the amount of blood through milliliters, ejection fraction refers to the percentage of the amount of blood that is ejected. So usually the EDVV is around 150 milliliters. The ESVV is around 50 milliliters. While the ejection fraction is usually around 65%. But it can increase if the heart is more efficient. So here we can see I've summarized the parameters that I've mentioned earlier. Again, if exercise increases, heart rate increases, stroke volume increases, EDVV increases. Yes, it increases. ESVV decreases. Okay, why does it decrease when exercise increases? Usually, ESVV decreases because, as I've mentioned, it refers to the amount of blood that stays within the heart after systole, after a contraction. So what happens after a contraction again? You pump blood out of the heart. So if you have a lower amount of ESVV, that means you've pumped a higher amount of blood out of the heart and into the body. Right? That makes sense? So that's why it decreases with the increased intensity of exercise. And lastly, ejection fraction increases because again, it's related to EDVV. Alright? So let's move on. I'm actually going to discuss now the Frank-Starling law. So the Frank-Starling law, I've provided a very simplified definition of it. An increase in the length of the myocardial muscle fibers can result in a stronger contraction. So think of a rubber band. When you get a rubber band and you try to, say, stretch it, and then you stretch it so far, then you release. What do you usually observe when that happens? It can fly out. It can catapult itself to another area in the room, right? This is similar to the heart. If the muscle fibers of the heart is stretched and it's contracted, then if that releases that stretch, that lengthening, then it would result into a catapult or a stronger contraction. This is basically what I was telling you about regarding ventricular distensibility and contractility. If the heart is able to lengthen and stretch at a larger pace or a larger length, then once it contracts, it would be a lot stronger than if it can only contract a little bit, only lengthen a little bit. So that is our infamous Frank-Starling law. Frank-Starling law. Okay, we've discussed oxygen consumption, heart rate, cardiac output, stroke volume. Oh wait, not cardiac output yet. That would be later. Sorry, that's a spoiler for later. We've discussed stroke volume, oxygen consumption, and heart rate. Now I want to go back to stroke volume again because we love stroke volume, right? Let's answer this question. Which do you think is a position better for an increase in the stroke volume. Again, as I mentioned earlier, a stroke volume is the amount of blood pumped by the heart with each contraction. So, which do you think? Would it be higher in lying down or standing up? Okay, I'm going to reveal the answer. It is, if you answered Chris Redfield, yes. Right, the correct answer is actually standing up, right? Why? Because stroke volume increases with maximum exercise, right? When you exercise at a higher intensity, stroke volume would also increase. However, when you are exercising in an upright position, meaning the gravity would help pull the blood down to your lower extremities, right? Because you're standing up. It would pull it into the lower extremities. Muscles would take more action via contractions to assist venous return. It would help the blood return more back to the heart, right? That makes sense, right? As compared to, let's say, you're exercising laying down like this in a prone sort of position. You would have a harder time to have an increase in stroke volume because gravity is not assisting. The muscles are not contracting as much because you're basically in line with gravity at this point. That's why we prefer for patients to be trained in an upright position. Not only because this increases as stroke volume, as I've explained, but it also helps in letting them adjust more to performing functional activities in their daily lives. Because we don't do ADLs, activities of daily living, while lying down, right? We don't do that. We usually do it in upright position. When you're eating, usually in an upright position. When you're writing something, usually in an upright position. You're dressing up, usually in an upright position. So it's better to train patients, not only because it helps with the ADLs, but it also increases their stroke volume, which is usually our goal in exercise. Because the higher our stroke volume is, the higher amount of blood is being pumped out, meaning they would have a healthier heart. Eh? Make sense? Chris Redfield? I think. Do you agree, sir? Hopefully you do. All right. Let's go to the last, well, not really the last part, but this is nearing the last part before we move on to another topic. Cardiac output, represented by the letter Q. Cardiac output is different from stroke volume because it is based upon not only the contraction of the heart, but the whole cycle of the heart rate. So you calculate cardiac output by finding the product of heart rate and stroke volume. So for example, if your heart rate is, let's say, 75 and your stroke volume is, let's say, 65. So your cardiac output would be around 4,000, right? Because usually it's calculated using a multiplication system. Usually the cardiac output is, wait, I just made a mistake. I'm so sorry. It's not 4,000. I was like, why is that so high? It is not 4,000. You have to convert it to liters. Okay, I'm sorry. I'm not great at math. But basically, cardiac output is usually heart rate, so beats per minute, and then stroke volume, which is usually converted to liters first before, not milliliters. So wait, let me convert it first. So let's say your stroke volume is 65 milliliters. Then we convert it to liters would be 0.065. right? And as I mentioned earlier, your heart rate is 75. So your cardiac output would be at 4.875 or 5 liters. Sorry about that. I am very idiotic. Okay, that's not a word. What am I saying? Okay, so that's actually 5 liters per minute. It's actually the resting value for cardiac output. So, yep, yep, yep. So, based on what I've mentioned earlier, using this little table here, what do you think is the effect of an increased exercise intensity with the cardiac output? It increases. Yes, that's true. Hopefully, you answered correctly. So, with cardiac output, it increases with exercise intensity. So here we have another graph. If cardiac output in the y-axis, oxygen consumption in the x-axis. So, yep, similar to heart rate and oxygen consumption, it increases first, but you see here, it's not a linear increase. We have a little tuk, it goes like this. It doesn't go like a straight increase. Why? You can see I've already marked here due to stroke volume. Since stroke volume is amount of blood pumped per contraction, usually with our cardiac output, it would state a little bit of ink here since it since we have a plateau for stroke volume, right? The graph I showed you earlier, where was it? This little guy here, right? Because of the chamber size, the stroke volume can increase like that. It goes like this because of chamber size of your heart. So that affects cardiac output. Why? Because cardiac output is the product of heart rate and stroke volume. So it has a little here. Okay, next. Oh, this is what I've mentioned earlier. Yep, yep, yep. Oh, I forgot to mention that blood is redistributed during heavy exercises due to changes in the circulatory demands of the body. So again, when we exercise, the amount of blood circulatory demand actually changes. So here I have a table that summarizes all the values. You can memorize it if you want. You don't have to memorize it, but it would be nice to know which ones increase and which ones decrease. An important thing here, actually, I want to note is the kidneys. So when we exercise, we don't actually have an urge to urinate as much as when we're not exercising. Why? Because as you can see here, from 19% of blood supplied, 3%. So you don't really need to urinate. However, in patients with hypertension who are usually taking diuretics that would increase the rate of urination, this would this blood redistribution does not really affect their kidneys. They would still have an increased rate of urination. That's why it's important when patients who are hypertensive, it's very important to remind them to drink water. I mean, everyone should drink water and prevent dehydration, but it's more important we watch out for any signs of dehydration with patients of hypertension because it's very important to watch out because things can change very quickly. You have to act. Yeah, it's better to prevent than to cure. So, we finished part one, or I guess this would be split into two parts. So, this is the first two parts of the systemic response to exercise. Very nice, and we've discussed a lot. And I just wanna look at Chris here. Just give me a second. Hello, Chris. Hello. Yes. Okay. What was I saying? Okay, so I'm gonna be posting a third part that would be discussing blood pressure and um respiratory response to exercise, which I think would be a lot easier to understand than blood pressure. So this is it for this video. I hope you learned something, and thank you for being here.